All right, today we are diving into a story that has been unfolding for literally billions of years. It's all about how our planet is constantly, and I mean constantly, changing its speed, and why that tiny, tiny change has shaped, well, pretty much everything we know about life on Earth.
It sounds like a trick question, right? What in the world could our moon, our celestial neighbor, possibly have to do with the actual oxygen you're breathing right now? Well, it turns out the connection is incredibly deep, it's ancient, and it is absolutely essential to our existence. The whole answer lies in the slowing rhythm of our planet's spin.
So to really get this, we've got to go way, way back. Because this isn't something that just started happening. No. This is a gravitational dance that began when the Earth and Moon were just kids. A cosmic ballet that has been slowing us down for eons.
You know, the force behind all this is surprisingly simple. The moon's gravity pulls on our oceans, right? That's what creates the tides. Well, all that sloshing water creates friction, and that friction acts like a constant, super gentle brake on our planet's spin, all while the moon itself is slowly drifting away from us. This has been happening non-stop for billions of years.
And you can actually see the results over geological time. It's amazing. We know from studying the fossil record that about 1.4 billion years ago, a day on Earth was only 18 hours long. Can you imagine? Even back in the time of the dinosaurs, a day was a whole half hour shorter than it is now. Today, we're gaining about 1.8 milliseconds every century. It's a crawl for sure, not a sprint, but it's the crawl that completely changed the world.
So this gradual planetary slowdown had this totally unexpected consequence. See, it gave a huge advantage to a tiny little organism that was about to pull off the greatest heist in the history of the planet, basically stealing the sky and filling it up with oxygen.
In the early oceans, there was this constant war being waged on these slimy microbial mats, kind of like the ones you can still find in places like Lake Huron. On one side, you had these purple cyanobacteria. They're the photosynthesizers, the ones that make oxygen. And on the other side, you had these white microbes that would come out at night and just munch on sulfur. They were in a constant battle for who got to be on top.
And their daily schedule was the whole key. When the sun went down, the sulfur eaters took over the top layer. But at sunrise, they'd retreat, and the purple cyanobacteria would start their climb up to the surface. But here's the catch, and this is so important. The cyanobacteria were, well, they were kind of lazy. They were late risers. It took them a few hours of sunlight to really get going before they could start pumping out oxygen.
And this is where the length of the day becomes the hero of our story. Think about it. On a short 18-hour day, by the time the cyanobacteria finally got over their morning lag and really started working, the sun was already on its way down. They just didn't have enough daylight. But as the Earth slowed down and the days got longer, that window of productive sunshine stretched out, letting them just churn out more and more and more oxygen.
The end result? A total planetary transformation. That slow lengthening of the day gave the cyanobacteria the winning edge they needed. They completely dominated the microbial war, and their waste product, oxygen, flooded the atmosphere. This event, the Great Oxidation Event, is quite literally the reason you and I are here, breathing, today.
But the effects don't just stop at the microscopic level. Not even close. A planet's spin doesn't just decide how long a day is, it actually determines its physical shape. So what did a slower spin do to Earth's figure?
Okay, so it all comes down to this thing called the equatorial bulge. The best way to think about it is like spinning pizza dough. You know how the faster it spins, the more it flattens out and spreads at the middle? Well, planets do the exact same thing. That centrifugal force from the rotation causes them to bulge out at the equator and get a little bit squished at the poles. And on Earth, that bulge is pretty significant. The diameter of the Earth at the equator is about 43 kilometers. That's almost 27 miles, wider than its diameter from pole to pole. So our planet isn't a perfect sphere at all. It's what scientists call an oblate spheroid. Basically, it's a little squat.
Now, just to put that into perspective, if you had one of those big classroom globes, about a meter wide, that entire 43-kilometer difference would be just over 3 millimeters. So it's a really subtle imperfection, but it has some very, very cool consequences.
For example, here's a great piece of trivia for you. Because of this bulge, the point on Earth's surface that's farthest from the center of the planet isn't the peak of Mount Everest. It's actually Mount Chimborazo in Ecuador, because it's sitting right on that equatorial bulge. And to bring it all back to our main story, as Earth's rotation keeps slowing down, that bulge is ever so slowly shrinking.
Okay, so a slower spin means we get longer days in a slightly rounder planet. Got it. But there's another absolutely critical system that's tied to rotation, the invisible magnetic shield that protects all of us from really nasty solar radiation.
So the best theory we have for how Earth makes its magnetic field is called the dynamo theory. And you can think of it like a recipe. First, you need ingredient 1, a liquid conductive core, which we have. Ingredient 2, a heat source to make that liquid churn around. Check. And ingredient 3, the crucial one, you need planetary rotation to organize all those churning currents and create a stable magnetic field. Without rotation, the whole recipe just falls apart.
So it follows that a major slowdown in our planet's rotation could weaken our protective shield. And we can actually see this play out elsewhere in the solar system. Mercury, for example, rotates incredibly slowly. One day there lasts 59 Earth days. And guess what? Its magnetic field is only about 1% as strong as ours. So, yeah, rotation is a key ingredient for staying safe.
For billions and billions of years, this whole slowdown story was driven by the gentle gravitational tug of the moon. But in just the last century or so, a brand new, powerful force has entered the picture, adding a really dramatic, modern twist to this ancient tale.
And that new force? Well, it's us. Recent studies from NASA have found that the rate that our day is getting longer is actually speeding up, and they've traced the cause directly to the melting of polar ice sheets and glaciers, all due to human-caused climate change.
The perfect way to understand this is the ice skater analogy. You've seen this, right? When a skater pulls their arms in tight, they spin way faster. When they spread their arms out, they slow down. It's the same principle for Earth. As our polar ice caps melt, all that water, that mass, flows away from the poles and spreads out toward the equator. This shift in mass is just like the skaters spreading their arms, and it's causing our planet's spin to slow down.
And the data on this is it's stark. Throughout the 20th century, the rate of slowing caused by these mass shifts was somewhere between 0.3 and 1 millisecond per century. But get this, since the year 2000, that rate has jumped up to 1.33 milliseconds per century. We are measurably, quantifiably speeding up the slowdown.
This quote here from NASA geophysicist Shirendra Adhikari just hits so hard. He said, in barely 100 years, human beings have altered the climate system to such a degree that we're seeing the impact on the very way the planet spins. It's not just a cosmic dance with the moon anymore. Our actions are now having a real, measurable impact on something as fundamental as the rotation of the Earth.
And that really brings us to the final thought here. The ancient, natural slowing of the Earth literally gave us the air we breathe. It was a change that paved the way for complex life. But now, as we contribute to a new, accelerated slowdown, it leaves us with a pretty profound question to ponder. What will be the legacy of the Earth we slowed down ourselves?